Hi, everybody. Well, you have your first distance learning test today. So to help get you ready, I thought I would show you how I would solve all the problems on the review homework. That's homework 18, review solutions. So here we go. All right, so welcome to 8.8. What have we learned about solutions chemistry? All right. So we've got the question of the day. The lesson is I'm going to go over homework 18. And then if you have any last questions, I'll just ask you one more time to shoot those my way via email or in class. And then your homework is to do the exam over GoFormative. All right, so the question of the day today. A pair of students wants to make a 1.5 molar magnesium chloride solution that is 2 liters. How should they make it? All right, well, the easy part is that we know it's 2 liters, so they need to get 2 liters of water. But if they want to make it 1.5 molar, how do they do that? That part's a little trickier. So we know we want the solution to be 1.5 molar magnesium chloride. All right, well, it's kind of hard to measure out 1.5 moles, but it's easy to measure out grams, right? So the first thing we're going to want to do is figure out how many grams is this. Well, we know molarity, but we don't actually know moles yet. However, we know that the volume is 2 liters. And you guys remember that molarity equals moles per liter. Just drawing in the magic triangle here. So we know molarity is 1.5. We know liters is 2. Let's solve for moles. That'll be molarity times liters. So 1.5 times 2 is 3 moles. And you can just check your work. Okay, yeah, 3 moles over 2 liters would be 1.5 molar. So we did our math right. All right, so we went 3.0 moles of magnesium chloride, but it's a lot easier to measure out grams. So let's just change those moles to grams. So if you have a unit that has to go, you put that unit down below. Have a unit that you love, you put that unit up above. So the number of grams here is going to be the gram formula mass. And if you just take a look at any periodic table, the mass for magnesium is 24.3. Just write that down here. 24.3. And chlorine is 35.5. But there's 2 of them. So I'm just going to use my calculator for that one, although you'll probably do it in your head before I finish. All right, I got 95.3 grams per mole. Let me just check my work. 5 times 2, yep, it's 24.3. Okay, great. All right, so that's the gram formula mass. I'll put that right here. 95. All right, so now I will just say, multiply that by 3. It'll be 285.9. So it looks like we had 2 sig figs to begin with, so we'll call that 200 and, oh wow, yeah, 200, oh gosh, that's almost 81. We'll say 280 grams. So to make the solution, they'll just take 280 grams of magnesium chloride, put it in 2 liters of water, and boom, they've got themselves a 1.5 molar solution. All right, so today I'm going to show you how to solve all the problems on homework 18, the review of solutions. So first problem, in a true solution, the dissolved particles are A, visible to the eye, B, will settle out on standing, C, cannot be removed by filtration, or D, are always solids. This comes from our first lesson when we looked at the definition of a solution. And one of the ways you can tell if it's truly dissolved down to the ion or molecular level is if you can tell that light can pass through it, if you shake it and nothing falls to the bottom or floats out of the top, or you pour it through a filter and nothing comes out on top of the filter. So that would be C, cannot be removed by filtration. Two, when magnesium chloride dissolves in water, the attraction between the particles that allows it to dissolve so well is, right, so we're thinking, what is the attraction between magnesium chloride, the solute, and water? Well, water, H2O, is polar. Magnesium chloride, that's a metal and a nonmetal, so that's ionic. So the attraction between something polar and something ionic is called an ion-dipole force. It's one of the types of dipole-dipole forces. All right, 3, when temperature is increased, the solubility of a gas in a liquid is blank, while the solubility of a solid in a liquid is blank. All right, for this question, I'm going to think of some examples. So a gas in a liquid, I'm going to think about the bubbles in a soda. If you heat it up, are the bubbles better at staying in, or do they escape? They escape. That means their solubility decreases. Okay, for a solid in a liquid, I'm going to think about cooking soup. When I cook soup, I'm going to heat it up to get the solids to dissolve more. So heating it up increases the solubility of a solid in a liquid. So that would be B. Solubility of the gas is decreased while the solubility of the liquid is increased. All right, number 4. When pressure is increased, the solubility of a gas in a liquid is blank, while the solubility of a solid in a liquid is blank. Okay, now we're thinking about pressure instead of temperature. I'm going to think of examples again. So for pressure, again, I'll think of, for a gas in a liquid, I'll think again about the soda can. To keep the bubbles in, you want to increase the pressure. That means keep the can of soda closed. So they're saying pressure is increased, the solubility of the gas in the liquid will increase. It keeps the bubbles in better when the pressure is high. All right, for the solid in a liquid, I'll think about soup. Increasing or decreasing the pressure doesn't change the solubility of the solid in the liquid. So for that one, the answer is C. It is neither increased nor decreased for the solid, but it's increased for the gas in the liquid. Okay. 5, a 2-liter beaker of water containing 4.8 moles of sodium hydroxide solids. That's not quite a complete sentence, but it says, what is the molarity? Moles per liter. All right, I know the equation for molarity is moles of solute over liters of solvent. So this has 4.8 moles. So that'll go on the top. And 2 liters. So 4.8 over 2, I can do that in my head. 2.4 molar, or 2.4 moles per liter. Okay, 6, which phrase describes the molarity of a solution? 1, liters of solute per mole of solution. Nope, that's backwards. 2 liters of solution per mole of solution. Nope. 3 moles of solute per liter of solution. Yes, there it is. And then the last one is moles of solution per liter of solution. Also wrong. Okay, 7. Which aqueous solution of potassium iodide freezes at the lowest temperature? For this one, I'm thinking about boiling point elevation and freezing point depression. The more solute added to a liquid, the lower its freezing point gets. So here I'm looking for the most concentrated solution. So here we have 1 mole, but here we have 2 moles. And we have 1 mole again, 2 moles. So it's got to be one of these ones. I'll cross out the others. This is 2 moles in 500 grams of water, whereas this is 2 moles in 1,000 grams of water. So this one, the moles will be a little bit more spread out, so its effect will be more dilute, but this one will be a lot more concentrated. So this one will freeze at the lowest temperature. All right, so we've got an unsaturated solution made by completely dissolving 20 grams of sodium nitrate in 100 grams of water at 20 degrees Celsius. In the space in your answer booklet, show a correct numerical setup for calculating the number of moles of sodium nitrate, gram formula mass, 85 grams per mole, used to make this unsaturated solution. So I have to show, how do we calculate moles? Okay, well, we know grams, and they tell us gram formula mass. So that actually makes it really easy. Let's start with the moles. 20 grams. Sorry, start with the grams, 20 grams. Okay, if you got a unit that has to go, where do you put that unit? Down below. Have a unit that I love. Put that unit up above. They tell us the gram formula mass is 1 mole weighs 85 grams. So it actually just says show a setup. It doesn't say find the answer. So I'm going to leave it at that. All right, for number 9, it says determine the minimum mass of sodium nitrate that must be added to this unsaturated solution in order to make it saturated. Okay, I'm going to look at table G for this one because that shows how many grams of something you need to dissolve in water to make it saturated solution. So we've got 20 grams of NaNO3 at 20 degrees Celsius. So here's NaNO3. Here's, looks like that's 20 degrees Celsius. So 20 grams, or to be saturated, we'd need, it looks like, about 88 grams. Right now, we've only got 20 grams dissolved. So to make it saturated, 80 minus 20 will make up the difference here. 68 grams, approximately, based on the graph. So about 68 grams more to be added to make it saturated. Number 10 says, identify one process that can be used to recover the sodium nitrate from the unsaturated solution. This is a review question that goes actually way back to the first unit of the year when we were studying ways to separate mixtures. They're saying, what's one way you can get the NaNO3 back out of the water? That's a mixture separation question. So we learned about distillation, filtration, and chromatography. For this one, since it's so well dissolved, we know we can't filter it to get it out. So that means we're going to want to distill, or in other words, boil the water. I can't really think of a way chromatography would be helpful here, so I think distillation is the way to go. Just boil the water and leave the NaNO3 behind. All right. This question says the boiling point of a liquid is the temperature at which the vapor pressure of the liquid is equal to the pressure on the surface of the liquid. You guys know that? Then it says the heat of vaporization of ethanol is 838 joules per gram. A sample of ethanol has a mass of 65 grams and is boiling at 1 atmosphere. Based on table H, what is the temperature of this sample of ethanol? Okay, so let's look at reference table H. Vapor pressure of 4 liquids. Oh, I think I put that in the, oops. Ah, I forgot to put it in the slideshow. Let me grab it real quick. Sorry about that, guys. Okay. Is okay. So let's take a look at table H here and figure out how we can tell what the temperature is. All right, so it told us that the heat of vaporization is 838. That's not very helpful. It tells us the mass, that isn't helpful. But it tells us that it is boiling, and it tells us the atmospheric pressure. And we know that the boiling point is when the vapor pressure is equal to the atmospheric pressure. So that means that if this, it's ethanol, right? Yeah. If this ethanol is, oops, boiling at 1 atmosphere, which is 101.3 kilopascals, it's right here. So that means it is about 80 degrees Celsius right now. Okay. For number 11, it says to calculate the minimum amount of heat required to completely vaporize this sample. This is also a review question from the very first unit of the year when we studied heat. There are 3 heat equations on the back of, oh, there's table H. Oh, well, on the back of your reference table. And Q equals mHV is the one we want because it says how much heat does it take to vaporize. So I'm going to use that equation. Q is the heat, M is the mass, HV is the heat of vaporization. So they told us everything we need. They told us the mass, and they told us the heat of vaporization for ethanol. So we'll just multiply those two. So I've got 65 grams times 838 joules per gram. And putting that in my calculator, that makes 54,470 joules. Looks like we have 3 significant figures, so we'll call that 54,500 joules. Or if you wanted to put it in kilojoules, 1, 2, 3, 54.5 kilojoules, just for fun. Okay. All right. Next question. This is about hydrogen peroxide, H2O2, which is a water-soluble compound. The concentration of an aqueous hydrogen peroxide solution that is 3% by mass, H2O2, is used as an antiseptic. When the solution is poured on a small cut in the skin, H2O2 reacts according to the balanced equation. The question says, calculate the total mass of H2O2 in 20 grams of an aqueous hydrogen peroxide solution that is used as an antiseptic. Your response must include a numerical setup and the calculated result. All right, so we want to find the mass of H2O2 in 20 grams of solution. we know the solution is 3% by mass. So if I were to use the equation for percent by mass, that's percent by mass equals the mass of the solute over the mass of the whole solution, which in this case is 20 grams, times 100%. Okay, so right now I'm solving for this. I don't know what this value is, so we can call that x. So to solve for x, I want to get it by itself. So I'll divide both sides by 100, and I'll multiply both sides by 20. And that's going to give us 0.6 grams of hydrogen peroxide in 20 grams of solution. Next question, determine the gram formula mass of H2O2. All right, this is also a review question. For this, I just look on my reference table and remind myself of the mass of hydrogen and oxygen. Hydrogen weighs 1. There's 2 of them. Oxygen weighs 16. There's 2 of those. So 2 times 16 is 32 plus 2. It's going to be about 34 grams per mole. Great. All right, last questions. When a person perspires, that is to say they sweat, the body loses many sodium ions and potassium ions. The evaporation of sweat cools the skin. After a strenuous workout, people often quench their thirst with sports drinks that contain sodium chloride and potassium chloride. A single 250 gram serving of one sports drink contains 0.055 grams of sodium ions. In the space in your answer booklet, show a correct numerical setup for calculating the concentration of sodium ions in this sports drink expressed as percent by mass. All right, so the percent by mass equation is going to be mass of the solute over mass of the solution times 100%. So mass of the solute looks like right here, 0.055 grams of sodium ions. Mass of the whole drink, 250 grams. Divide those times 100%, that gives us 0.022% in your sports drink. 15, describe the transfer of energy between the skin and the surroundings as a person sweats. This is a review question from Unit 1, also when we learned about heat. So the question is a lot more simple than it sounds. They're asking, where does the energy go? Is it that the cold comes into your body, or is it the heat leaves your body? It's that the heat leaves the body. And goes to the surroundings. Okay. Number 16, in the space in your answer booklet, draw a Lewis electron dot diagram for one of the positive ions lost by the body as the person perspires. This is a review question from Unit 3 when we learned about bonding. So let's find one of the positive ions lost by the body and then draw a Lewis dot diagram. So we know that, that the body is losing these guys, and it says the body loses specifically sodium ions and potassium. So we could choose either one of those and draw the Lewis dot diagram. So let's say you picked sodium. The symbol for sodium is Na. Usually it has one valence electron, but when it's an ion, it has lost that valence electron. So now it has no dots. You could just draw the brackets and the positive sign. Very similar with potassium. If you picked potassium, its symbol is K. It has one valence electron normally when it's an atom, but when it's an ion, it's lost its only valence electron. So now it's a positive ion. Awesome. All right. So that's it, you guys. Your homework is to do your test. It's on Go Formative. It's an open note exam. You can use your reference tables, a calculator, any of the PowerPoints or videos from class. You can complete it on GoFormative, and you'll have from the end of class Thursday until Sunday to complete it. And I do just want to remind you to please be sure and do your own work. It's open note, but it's individual. I want to see what you've learned about solutions in this time of distance learning. All right, thank you guys. That's it. Have a wonderful rest of your day.